Hey everyone, and welcome to the Retro channel, and today we are repairing 3 broken Commodore 64s and checking out a bunch of power supplies. This is going to be a repairathon, but rather than splitting it into multiple videos, we're going to get all this done in this single video. And I'm going to try and make this as beginner friendly as possible, so we're going to avoid trying to use the oscilloscope for most of this. We're pretty much just going to be relying on a multimeter and some basic soldering tools. I'll also be going through basics of how to use a soldering iron and a multimeter. The idea is that if somebody is just starting out in repairing these machines, maybe you've come across a bunch of them and aren't sure what to do, watching a bunch of videos on YouTube with people using oscilloscopes and stuff probably isn't going to help you, because you may not be that far into your repair journey just yet. So I'm going to try and keep this all as basic as possible, explain as much as I can in the simplest possible terms, and only rely on the most basic tools. Now you may also notice the runtime on this video is pretty long, and that is because, like I said, I'm trying to cover as much as I can, especially for beginners, but even if you're an old hand at this thing, you might pick up a few tips and tricks along the way. And of course, hopefully it'll be just entertaining to see all of these get repaired. So yeah, feel free to watch this at 1.5 or even double speed if you like. Personally, I do that with a lot of videos that I watch these days, so I won't be offended. So here we have a number of Commodore 64 power supplies, and these all basically do the same thing, even though they look slightly different. They take mains voltage, run that through a large transformer, and from that we get a 9-volt AC output, and it is also rectified and regulated to a 5-volt DC output. The potential problem with these is they're all very old and they were built to a very low cost. So these can end up failing, and they can sometimes do it in a way that will actually destroy the chips in your Commodore 64. So before you even try and plug one of your machines in, you should always check the power supply to make sure you're getting the right voltages out of it. Now, if you've ever looked online for tips for where you can start with a Commodore 64, the first thing you're probably going to come across is check the power supply. And that's fair enough, because like I said, these can fail. Although in saying that, I've never actually seen one of them actually fail. I'm not saying the stories you read online about the Commodore Brick of Death are untrue. I'm sure some of them have actually failed and possibly taken out the computer with them. And even when I first started out, I always recommended people avoid using the original power supply. I think I even went as far as gutting one of mine and putting a switch mode in there, even though the original components were working perfectly fine. So I wouldn't say you should throw these away or completely avoid them. In fact, I use an original brick for my Commodore 64 and it works just fine, and I trust it to work well into the future. Although I will say, with this particular style brick, the black version of these, which I think only came out in North America, do tend to fail from what I hear. So if you're in the US or Canada and you've got one of these black versions of this brick, you definitely want to check that before plugging it into the computer, and certainly keep on checking it periodically to make sure it's still outputting the correct voltages. But dare I say, all of these are going to be just fine. But we're of course going to check them before we plug them into anything. So let's start off with this one here. As you can see, the case is a little bit warped compared to the other one that we've got. So yeah, these do get quite warm, and obviously that can also lead to failures, but I reckon this thing is going to be just fine. Let's plug it in, see what happens. All right, well, it is now plugged in, and like I said, there's only 9 volts AC and 5 volts DC coming out on this connector, so it's not like mains voltage. In fact, the large transformer isolates you from the main supply, so you can safely touch the pins in here. You're not going to get a shock. I wouldn't go sticking your tongue in there, but if that's your thing, go right ahead. Let's grab our multimeter. This is a fairly fancy one, but any basic multimeter should do the job. And we want to set it to volts DC. Now, because I don't have 3 hands, I'm just going to stick this cable in through here. That should be enough to sort of secure it in place while I hold these probes. And because these probes have quite a bit exposed and I don't want to risk shorting these pins together, I'm just going to throw a little bit of sticky tape over the end of these probes, just so the tips are only exposed. Regular old sticky tape, nothing fancy about this. And just going to put it just around there. Doesn't need to be pretty, as long as it's somewhat secure. There we go, that'll do. Another option is to use a little bit of heat shrink tubing, so stick that over one of the pins, obviously cut it down to size, and then you can safely probe it that way without covering up these probes. Either way works, and I imagine a lot of people are not going to have heat shrink on hand if they're only just starting out. So with our multimeter set to volts DC, we want to put the black probe in this pin right in the center at the bottom, and the red probe on the pin just to the left of it. And as you can see, we're getting 5.191 volts. That is perfectly fine. Usually you'll get a little bit over 5 volts, but what we're looking for here is nothing above, say, 5.5 volts. This voltage will drop a little bit when it's actually connected to the computer because it's drawing a little bit of power. So yeah, anything around 5.2 volts is pretty average. Now, like I mentioned, there is also 9 volts AC being output by this power supply, so if we set our multimeter into AC mode, we can find our AC voltage on these top 2 pins, and it doesn't matter which way around you've got the probes because it's AC voltage, so polarity doesn't matter. So if we measure here, we should see probably around 10 volts. 9.9. There we go, there's our 10. Usually around 10 volts, maybe you'll get 11 volts. Once again, that's fine. The AC output is practically never a problem, so you don't necessarily need to measure that. Unless you've got nothing on the DC output, then you should go back and check the AC output, because the DC supply is actually generated by the transformer inside, which is also generating the AC supply. Hopefully that all made sense. Now, while I've still got this power supply plugged in, we may as well check it under load. So this is a little board that I just sort of bodged together. Basically what it does is put a 4.7 ohm resistor on the 5 volt DC output and a 10 ohm resistor on the 9 volt AC output. That'll create a current draw of roughly 1 amp on both the DC and AC outputs of this power supply. And sometimes you can measure a voltage perfectly fine with no load, but once you actually apply load to it, you may see those voltage rails go down or lower in voltage. As you can see, plugging it in here, it's now saying 5 volts on the DC output, or 4.9 volts. And like I said, that is due to, a little bit of extra load on there. Usually will bring the actual voltage output down. So if I measure across this resistor up here, we're seeing basically the same as this display, 4.92 volts. Once again, that is perfectly fine for this power supply. You'll notice that there's no current displayed here. That's just because this meter is broken. And of course, if we measure across the AC side, we're probably going to see something closer to 9 volts now that there's a load on there. 9.2. So I'd be more than happy plugging this particular power supply into my Commodore 64. Of course, maybe every 6 months or a year, I'd double check those outputs again, but I don't see any reason to freak out and go throwing this thing away. All right, let's check out this wedge-shaped one. We'll plug it in. And you can see that the owner of this recently checked the 5 volts DC output and got 5.17 volts. So that's always a good sign, but we'll double check it just in case. Oh, and you'll also notice on this one, yes, very cheaply made down to a cost, because they've only included the pins that have the actual voltage outputs on them. Interestingly enough, you'll notice that it's the pin to the right that's actually populated on this one, whereas before we were measuring from the pin to the left. Most power supplies have the 5 volts on the pin to the left, but sometimes it is the pin to the right of center. Either way, if you don't see DC on one of them, then check the pin to the right of the center pin. One of them should have your 5 volts DC, and if it doesn't, then you've got bigger problems. The pins on this are a little bit crusty, so you might not get a good reading if we don't have proper contact. Yep, once again, 5.2 volts, perfectly happy with that. So I'm going to plug this into my little load. Like I said, you don't necessarily need something like this. It just helps confirm our suspicions that this power supply is fine. I'm going to spray a little bit of contact cleaner into this thing. And yes, the power supply is still on. This contact cleaner is not really conductive, so no issues doing it that way. And I'm just going to use my little plug on this board just to sort of clean up those contacts a bit. Of course, if you don't have something like this, contact cleaner or 99% isopropyl alcohol and say a toothbrush and just get in there and give it a good scrub should also do the trick. So once again, we can see our DC side, it's actually only dropped to 5.1 volts. We can confirm that with the multimeter, 5.13. And of course our AC side should be around 9 volts at the moment, 9.24, all good. We'll skip trying to probe the pins on this one. We'll just plug it straight into here and see what happens. Ooh, 4.6 volts is a bit low. Let's just confirm that. 4.63, 4.65. Could be dirty contacts on this plug, but they look pretty decent. Yeah, still the same, around 4.6. Let's check the AC. That's about right, 9 point something. Is it going to climb up there? 9.3. So this isn't necessarily dangerous to use with a Commodore 64, but it could cause issues. That voltage is a little bit lower than I'd like to see. One more trick we can do is put our multimeter into AC mode and actually measure this DC output. Ideally, we should see 0 volts here because a DC voltage shouldn't have any AC component. And as we can see, it is 0 volts. If you measured some sort of voltage AC, maybe 0.1 of a volt is probably fine, but anything above that would indicate an issue with the regulation of the DC voltage inside one of these power supplies, and once again, it probably shouldn't be used. But at the moment, this seems mostly okay, although, yeah, that DC output is a little bit low. It's not going to be dangerous, but it may cause stability issues with the Commodore 64. Let's just see what that looks like without a load. So center pin and pin to the right. Okay, so on this power supply, the pin to the right is not connected, so we're seeing 0 volts. If we measure from the center pin to the pin to the left, yeah, almost spot on 5 volts. Once again, as we saw with the other supplies, that is a little bit low. We'd expect to see closer to 5.1, 5.2-ish. This one is questionable. Right, finally, this brick. Now, like I said, the North American ones that are black potentially might be bad, so you definitely want to check them if you've got one of those bricks. As for these ones, which are normally more of a cream color, you can see this one is slowly turning orange. I've never found an issue with one of them, but well, I guess we're about to find out if this one's okay. In fact, well, it tested at 5.04 volts, so chances are it is. Let's go straight for our dummy load. Looks like it's holding up pretty well. And our multimeter confirms that. You'll notice it says negative on the multimeter. That's just because I've got the probes around the wrong way. So I'd say at the moment, all of these power supplies are perfectly safe to use. I don't see any reason not to, but like I said, you probably want to check them periodically, maybe every 6 months or a year, just to make sure that DC voltage isn't going higher than, something around 5.2 volts. As for this one, it's still safe to use, but that low DC voltage may actually cause some stability issues. We're not going to find out until we actually try and power a Commodore 64 with it. All right, let's take a look at these machines. I think we'll start off with the 2 bread bins, and they're called a bread bin because they sort of resemble a bread bin where you store your bread. And then we'll check out the 64C because I think this will be slightly different. Obviously, as you can see, the keyboards between these 2 machines have been swapped over. And yes, that is perfectly fine to do. There are some other differences between these machines that you cannot swap over. But we'll get to that when we actually check out the 64C. Let's first check out these 2. We'll start with this one. Now, what I normally do before even powering one of these on is actually open it up and take a look on the inside, just to make sure everything looks above board. One thing I'd highly recommend doing before opening one of these up is making sure you don't have a build-up of static electricity on your body. An easy way to get rid of that is to touch a metal door handle or say a basin tap, and that should get rid of any static. Just make sure you don't go rubbing your feet across the carpet when you come back to the bench. You'll probably see a lot of people wearing an anti-static wrist strap, and you'll notice that I don't have one, and that is because my actual bench mat here is an anti-static mat. So this thing is actually connected to ground through a fairly high ohm resistance, but anytime I touch this mat, I'm basically discharging any static electricity. So seeing as I'm always touching this thing, I don't really have to worry about the wrist strap. Now, normally to open one of these up, you'll find 3 screws on the underside that need to come out. Looks like these have already been taken out, so don't have to worry about that. And then you just need to lift carefully from the front of the machine, and once you reach sort of 90 degrees, you should be able to lift the cover off. You'll notice that there's some clips at the back here which usually break off. It looks like these 2 have already broken off, and they clip into the back of the bottom case here. So yeah, just be a little bit gentle with these when you first open them up, because like I said, those clips will easily break. Now the next thing you'll probably encounter is one of these RF shields. It'll either be a piece of shiny cardboard like this, or a metal shield. But either way, what I recommend doing is basically taking these off. This one is usually clipped over the cartridge port like that. Taking them off and throwing them in the bin. They don't really serve any useful purpose. I think they were just originally put there to pass some FCC regulations, and these days it's really not worth keeping these. All you're really doing is trapping heat inside the machine by leaving them in. So if we fold that back, we get our first look at the board in this machine, and there are a number of different board revisions. Usually if you look towards the bottom of the board, you'll find the actual revision, and this one says assembly number 250407. This is a fairly early revision of the Commodore 64, but most of the basic troubleshooting we're going to do, you should be able to apply to any revision of these boards. Now looking around on this board, everything seems to be okay. All the chips are in place and they look to all be in the correct location. Of course, if you're not sure, you can easily Google the assembly number of your board and find a picture of what it's supposed to look like. The main thing you want to watch out for is with any chips that are in a socket, first make sure they're in the correct position. So the 6581 on these boards, which is the SID chip, should be at U18. Keep in mind with different assemblies, the SID and this chip up here, which is the PLA at U17, could be in different locations on the board. So one thing to remember is U18 will always have the 6581 SID in it, and U17 will have the PLA. This chip can sometimes be marked with different markings. As you can see, this one says N82S100N. This is one of the older style PLAs. Some of these will say 906114, but either way the PLA should be at U17, the 6581 SID should be at U18. You also want to make sure the orientation of all these chips is correct, and on the Commodore 64, if you notice these little notches at the top of the chips, they should all point towards the back of the machine. Now, while I'm in here, I am going to take out all of these screws to release the actual board because I want to get rid of this cardboard RF shield. On the ones that have a metal shield, you usually have to desolder the RF shield in order to get it off the bottom side of the board. But usually for Commodore 64s in PAL regions, so Europe, Australia, pretty much everywhere except North America, usually you'll find one of these cardboard shields. And one of the first things I like to do with these, once I've got the screws out, is lift out the board and throw that in the bin. And seeing as that's out of the way, we can also take a look at the underside of the board, and yeah, everything here looks pretty normal. You can see that this part of the board is a little bit more discolored. That's just from heat buildup, probably from this voltage regulator here. But nothing really to worry about. It happens with age and heat. You may also notice there's a little bodge wire between these 2 pins here, and that is also perfectly normal. Nothing to worry about there. While we're here, we may as well check on the VIC-2 chip, which is under this metal can, just to make sure it's also in its socket correctly. And these are usually pretty easy to open up. You just sort of pry at them a little bit and the cover should pop off. And there is our VIC-2, and as you can see, it's an older VIC-2 in a ceramic package, whereas the newer VIC-2s look more like these things in the plastic package. And one other thing I can spot straight away, is this sort of crusty stuff on the board around these two capacitors. This is actually a fairly common issue with the 407 boards, and it seems to happen more often than not when it's got a ceramic VIC2 installed. What I think happens is these two little electrolytic capacitors in here get cooked by the heat buildup from the VIC2 and eventually spill their juices. So yeah, this is a somewhat common failure with the 407 boards, and also the fairly rare KU14194HB boards. Yeah, that really rolls off the tongue. Yeah, if you find a ceramic VIC2 in these and these little capacitors, you definitely want to check on them to make sure they're not leaking. You'd probably just want to replace them as a matter of course. Now, if we had already plugged in the machine, I don't think it would have caused any real damage. With these capacitors in the state that they're in, we probably just would have got no video signal at all. These are part of the clock generation circuit, and the VIC2 actually produces the video signal that we see on screen. And if these two are out of commission, then chances are the crystal output, which is 17.73 megahertz, won't actually make it over to the VIC2, and therefore you won't actually get any video signal. So let's plug this machine in anyway and see if we actually get a video output, but I very much doubt it. So we'll plug in one of our power supplies. I'll use this one here because we know it tests okay, and I'm also going to make sure the power switch is off in the down position. Plug that in, and when it comes to video output options, you can either use the RF output if you've got a TV that has an analog TV tuner, which most people probably don't these days, or you can use this DIN connector, which actually has a composite video signal along with separate Luma Chroma or S-video, and of course audio signals. The problem with these things is, of course, you need a DIN cable to take advantage of that. Now, one option would be to build your own cable, but what I actually prefer these days is to use one of these. You can see it's got a 5-pin DIN connector on this end and 4 RCA jacks on the other. Now, this isn't perfectly suited to the Commodore 64 because not all of these jacks will actually have an output on them, but you can be assured that this one will be the composite video output and the black one will be your audio output. It's best to avoid plugging anything into these two until you know a little bit more about what signals you can expect on them. Of course, I'll leave a link in the video description to where you can find one of these. So we're only going to connect our composite video output, and I guess we may as well connect audio while we're at it, just in case. And if you've got a fairly modern TV, you may not even have RCA jacks like this on the back of it. Some TVs have a little 3.5mm, like your old headphone connector, that actually breaks out into RCA jacks. So you'll have to consult your TV manual if you're not sure. But what I'm going to be using today is the RetroTink 5X. This is like an analog video scaler, so it takes a number of different analog signals and gives us a HDMI output that we can pretty much plug into just about any display. There are plenty of other similar things like this. This one is relatively expensive. Of course, you can find much cheaper composite to HDMI converters on AliExpress or eBay or whatever, but some of them will do a really poor job. Some of them might not even work with the video output from the Commodore 64, so your mileage will definitely vary there. If your display has got RCA connectors on the back, definitely use those first. All right, so with everything plugged in, let's see what we get. Absolutely nothing, as expected. Normally the screen would turn black for a second and then we'd get our Commodore 64 basic screen, but as you can see it's currently blue, which means this thing is not even detecting a hint of a video signal, which is kind of what I expected. But seeing as we've got it powered on, we may as well do a couple more quick tests with the multimeter. So remember that our power supply outputs 5 volts DC and 9 volts AC. Let's see if we can find those present on the board, because if we don't find them, then we could have more issues than just these two capacitors. So I've got the multimeter set to volts DC, and we're going to go over to the user port connector, this one on the far left here, and we're going to measure from the right hand side these two pins with the gap in the middle. So Over here, if we stick one probe on this pin and one probe on the other, we should see our 5 volts coming from the power supply. And we do not. It's definitely switched on. Yeah, okay. So it looks like we may have other problems. We can also check our 9 volts AC coming from the power supply, and we can find that on these 2 pins on the left-hand side that also have that gap in between. So if we measure here, we're supposed to be seeing, 9 or 10 volts AC, but once again, we're seeing 0. So this machine appears to be completely dead. You can also feel some of the chips on the top to see if they're getting warm, and absolutely nothing is warming up here. So we could also have a busted fuse. Let's switch over to continuity mode, and with the machine powered off, we're going to check either side of this fuse. Oh, the fuse is okay. So I think we've got a couple of problems. Definitely these 2 capacitors have leaked. We can see that quite clearly, but we're also not getting any power from our power supply. So I have plugged in the correct power supply, and we did see voltages on this side of the plug, and at some point between the plug over here and our user port over here, our voltages are disappearing. Now this could be a problem with the connector itself, but I'd say more than likely it's a problem with the power switch. These are known to go bad due to the contacts inside just building up gunk and dirt and other corrosion. So let's put our multimeter back into continuity mode. So with the power cable unplugged, what we're going to do is put one probe on this center pin, doesn't matter which way around you've got these, and the other one on the pin closest to the power switch. And then if we flick this on, right now this multimeter should be beeping like that. And it is not doing anything. So that's almost certainly a bad power switch. We can also do the same on the other side of the switch. So once again, from the middle pin to the pin closest to the switch itself, flick that on, and yeah, we're getting nothing on that side either. We should basically be getting 0 ohms once the power switch is turned on. So we know for sure bad power switch, bad caps. Potentially there's other problems, but until we do something about this switch, we're not going to be able to get any further. Now, usually the way to fix this is to remove the switch, which does require desoldering it. And like I said, if you've got that metal shield over the bottom of your board, you're also going to have to remove that to actually get to the solder points of the switch. Sometimes the easiest way to remove those metal shields is just to find the little tabs that are soldered around the outside and basically snip through them. Now there is a chance we can get this switch working again without removing it from the board and potentially replacing it, or at least opening it up and cleaning it out, and that is to spray a little bit of contact cleaner inside it. Alternatively, once again, you can use 99% isopropyl alcohol. What I'm going to do is try and squirt some of this just behind this plastic part of the switch here, and hopefully get it into our contacts, which are in this part back here. Give that a bit of a dousing. And I'm going to tilt the board up this way and just exercise the switch. As I said, this may or may not work, and I wouldn't really consider it a long-term solution. Really what you should be doing is either replacing the switch or at least deconstructing it, which means removing it from the board and cleaning up the little contacts on the inside. But let's just see if this made any difference whatsoever. So again, we'll put one probe on this middle pin and the other one on the pin closest to the switch. And look at that. It appears to be working. Let's check the other side. Basically, this side at the front is for the 5 volts DC, and the 2 pins at the rear are for the 9 volts AC. So we need both of them actually making it through the switch in order for the machine to actually work. And yes, that is also getting through. Now you've got to keep in mind that a multimeter is putting a very tiny amount of current through those contacts. So with one of these, it may appear perfectly fine. We don't see any resistance. But when we go to put, say, 1 amp from the power supply through those contacts, we may still run into issues if they're still quite dirty. I guess there's only one way to find out. I'm not even going to worry about hooking up the video output just yet. Let's just see if we get our expected voltages over at the user port. So we'll start off with the AC reading, which should be on these two pins. And yeah, we're pretty much up to about 9 volts. That's a good sign. If those contacts were still quite dirty, we might get, 4 volts or 5 volts or something. But 9 volts is a good sign. Let's see if our DC also provides similar results. Yep, I've got the probe switched around the wrong way, so it says -5, but if I just swap these around, we do have 5 volts there. So this machine is now receiving the correct voltages and in theory should be working, but we know with these two caps, it's probably not. Let's see if we get any video output this time. Haha, we get a black screen. We don't get anything else, but we get a black screen, and that's probably the most common failure mode of these computers, and doesn't really tell you a whole lot about what's not working. Like I said, these two caps have obviously failed, so it's not worth, trying to troubleshoot anything else until we get these replaced. Let's get them out. So to replace these, we're obviously going to need replacements. So let's check the value of them, which you should be able to find printed on the side of the capacitor. And these ones say 10 UF 25V, so 10 microfarad 25 volts. Capacitors are pretty easy to find, but I'd really avoid getting them from like AliExpress or somewhere like that, because chances are they're going to be cheap rubbish and you'll eventually end up with probably leaking capacitors again. So I'd stick with places like DigiKey or Mouser or what's the other one? Farnell if you're in the UK. Somewhere like that. Try and stick with reputable brands like Rubicon is a good one, Nishikon, Panasonic. There's a couple of others, but those three are the main three that I try and use when I'm shopping for capacitors. And after a quick look through my stock of capacitors, I found some 10 microfarad 25 volt Panasonic branded caps. Of course, the other thing we're going to need is some solder. I like to use the Kester 6337 leaded solder. Pretty much any leaded solder should be fine for this job. I just avoid using unleaded solder as it's not really necessary, and it's a lot harder to work with that stuff. So stick with leaded if you can find it. You're also going to need some solder braid. I like the MG Chemicals Super Wick. This stuff is basically just fine woven copper with some flux impregnated into it, and not all solder braids are equal. Just like the solder that I use, this stuff is also fairly expensive, but I guess you get what you pay for sometimes. And of course, you're going to need a soldering iron. I'd recommend something that has a temperature control, and usually I have mine set to 330 to 350 degrees Celsius. No fucking idea what that is in Fahrenheit, but I'm sure you can figure that out. The tip on your soldering iron can also play a very important role. So when it comes to through-hole soldering, like when the actual leg of the component goes through the board, I'd recommend something like either a knife tip, which is what I normally use, or a chisel tip like this one. The reason for this is because when you're heating a joint, you want to make sure that you're heating the leg of the component and also the solder pad underneath. And you want to get as much contact between both of those points as possible. So with this chisel tip or the knife tip, you can see that there is a lot of contact between both the leg, the pad, and the soldering iron tip. What you want to avoid is using something like this. This is a conical tip and it's not well suited for through-hole soldering. So if I bring this down to the joint, you can see that only the very tip of this thing is actually making contact with the lead and the solder underneath. So at the moment, it's not even managing to melt the actual solder. I think it'll eventually get there, but you'll end up with a very poor quality joint. So I'd highly recommend getting a soldering iron. If it doesn't have replaceable tips, look for one that either has a chisel tip or a knife tip, or if it does have interchangeable tips, definitely swap out the tip for one of these two. So I'm just going to mark on the underside of the board where these capacitors are, so that's one of them there, and the other one is there, just so I don't accidentally desolder the wrong thing. Now, because these things have leaked, it may put up a bit of a fight. It seems that the electrolyte from the capacitors, when it mixes with the existing solder, seems to raise the melting temperature of the solder a little bit. So what I'd recommend doing is actually getting a bit of fresh solder and just trying to mix that in with the existing stuff there. It may take a few seconds to actually get things flowing, but hopefully they should mix together, and that'll make it a little bit easier to actually get this solder off the board and get these capacitors out. Normally you should only need to have your soldering iron on the joint for, say, a couple of seconds. But yeah, when cap juice has leaked into the solder, it may take 4 or 5 seconds to get things flowing. And when you are soldering, you want to heat the leg and the pad at the same time with the soldering iron and introduce solder from the opposite side. I'm just going to get some fresh solder into all of this stuff. And then we're going to come in with our desoldering braid, or alternatively, you could use a solder sucker pump like this one, but we'll try it with the braid first. And I'm going to put the braid over the top of that solder joint and come in with the soldering iron on the other side of the braid. And with any luck, the solder should start wicking up into the braid itself. So you can see it's removed quite a bit of that solder, and of course it's all in the braid now, so I'd recommend just cutting that bit off and starting again. And just keep going until all that solder looks like it's been soaked up. The reason I'm cutting this old stuff off is because once it's full of solder, it will quickly absorb all the heat from the soldering iron. In fact, you could even cut up just little strips of this braid and hold it with some tweezers, and that can also aid in actually wicking up this solder, because basically this soldering braid is like a big thermal mass, so it's going to be sucking heat away from the joint and away from your soldering iron tip. So the more you can avoid that happening, the easier it will be for the solder to actually start flowing. And notice that I always remove the soldering iron and the braid at the same time. What you don't want to do is remove the soldering iron first and then try and remove the braid, because as you can see, we've now soldered the braid to the actual joint. So always lift these off both at the same time. I think on that note, we can give these capacitors a little jiggle. Well, one of them's already fallen out. Where did that go? There it is. Yeah, it's corroded so bad that it's lost one of its legs. That can happen. Let's see if this other one... Yeah, this other one still feels tight, so it's still being held in. What I'm going to do is just keep jiggling it with one finger, and yeah, I can see none of these legs are actually moving. So, right, now that one's moving, and even trying to heat that up, that leg is not moving. Oh, there it goes. So I'm just going to keep jiggling that until the actual solder cools down, and we should be able to pull it out. Alright, and now we can see some of the carnage and also the remnants of that other leg. Let's see if we can clear that out, because we're going to need to get our new capacitor in there. So once again, some fresh solder, and you can see that it really doesn't want to take to that leg or the pad underneath. And that's just because of all that nasty old cap juice. So I'm just going to grab that leg with some tweezers and then heat the joint from the back. Hopefully. Ooh. Yeah, there it is. Let's try and clean this up just with a bit of 99% isopropyl alcohol on a cotton bud. And this side actually seems to have cleaned up okay. It doesn't look too bad, but you can see definitely this joint here and the other side look very dull, so that could be a problem. So let's just spray some isopropyl alcohol into this little cleaning brush here, which has been absolutely brilliant. Thanks to Lee from More Fun Making It for getting me onto these things. And just give this area a bit of a scrub. because once this cap juice leaks out, it can find its way into all sorts of nooks and crannies. And I think this chip here is no exception. You can see some of the legs on it are a little bit tarnished, but they might be okay. In fact, just running a tweezer across them seems to shine them up. We'll try polishing up some of these pads with a fiberglass pen. These are pretty easy to find. Just be wary when you use them that they will shed little fiberglass fibers. So try not to touch the area after you've been rubbing it with one of these, because you will get little fiberglass fibers stuck in your fingers. And if you get too close, potentially fibers stuck in your lungs. Right, those pads are looking a little bit better. This trace here actually looks to be okay. Usually the traces will actually turn black if they're starting to corrode, and I don't really see that happening here. So I think we got off actually quite lucky in this case. I can see that there's no traces leading off from either side of this capacitor here on the top side of the board, so nothing to worry about here. And on the other capacitor, there's no trace from this pad here, but there is definitely a trace from this pad over to this ceramic capacitor here, and that definitely looks like it's been eaten away quite a bit. I'm just going to try and scratch at it. Oh yes, there's a hint of copper under there. I think I might actually remove this capacitor as well. I don't think there's anything wrong with it, but it's just kind of in the way at the moment. Okay, well, we definitely got lucky with this one, because I think it was only that small bit of trace that was actually potentially compromised. All the other traces around here look to be okay. So let's put this little ceramic capacitor back in. It doesn't matter which way around these things go, because they don't have a positive or a negative. They're not polarized. The electrolytic capacitors, on the other hand, are going to be a different story. So I'm just going to try and tack that in, and then heat the pad and the pin at the same time and introduce solder from the other side, and done. Let's try and clean up some of this stuff here. I still need to remove that bit of solder that's stuck there now that that leg is gone. Right, well, that's a surprise. This pad is still intact. I thought it was completely gone, but it actually managed to survive. It doesn't look great, but it's there. Definitely got off lucky with this one. I've seen these caps do a lot more damage in the past. This trace here looks a little bit dark, so I'm just going to reveal a bit of that. Take this solder mask off the top of the trace. Expose the copper, and we'll just put some fresh solder over that once we put these caps back in. So let's get these caps in. Like I said, these are polarized, so you want to make sure that the positive side, which is usually the side without the stripe, goes into the positive hole on the board. The side with the stripe is the negative, so obviously don't put that in the positive hole. You can also tell by the longer leg on an electrolytic capacitor is the positive leg. So long leg in the positive hole. Sounds weird. This one shouldn't be a problem. Everything looks good on the underside, so easy done. Clip those legs off. Now for this one, we'll throw the capacitor back in, and then we'll try and just cover up some of this exposed copper with some fresh solder, just so it doesn't corrode on its own. And we're just going to get a bit of solder over that, just so it's not copper colored. Just going to try and get a bit of solder onto that trace and spread it around a little. Also onto this pad here. Yeah, even after doing all this, you can see these pads really do not want to take any fresh solder, so I'm Let's try again. I can feel that capacitor is very hot, so I don't want to mess around with it anymore. We have a decent, if not very pretty connection on the top side and the bottom side, so that's good enough. All right, let's give this another try, but I think we're still going to get a black screen. If you remember what I said before, these two capacitors, if they fail, mean that the clock signal from this crystal doesn't make it to the VIC2, and therefore we get no video output. But seeing as we got a black screen, which is technically a video output, I don't think these are the cause of that. I think there's something else that's going to be causing this black screen problem, but let's see what happens. Black screen, and still a black screen. Wah, wah, wah. Let's check these voltages again. So check over here, 5.05 looks good. And yeah, close to 9 volts AC. We can also check the voltages on these voltage regulators down here. These two are what supply the voltages for the VIC2 and the SID. But seeing as we've got a black screen, and as I said, the VIC2 actually produces the video signal, we know for a fact that it's definitely receiving some kind of voltage, enough for it to produce a video output. So if we stick our negative probe on ground, you can use the shiny part of the outside of the board or this heat sink over here, and the positive probe on the right pin of these voltage regulators. So this is a 7812, so we should have 12 volts coming out of the right pin on this one, and we do, 12.02. And on this one, which is a 7805, we should have 5 volts on the right hand pin, which we do. So yeah, this is definitely getting the correct voltages. We know that the clock circuit is working because otherwise we wouldn't have any video output at all. One more thing we can check with the multimeter just to rule it out is making sure the CPU, which is the 6510 in here, is not stuck in reset. So normally when you first power on the machine, the CPU is held in reset for about a second or half a second, just until all the voltages stabilize, and then it comes out of reset and starts executing code. So on the 6510, which is a variant of the 6502, pin 40 of the CPU is reset. Remember that we had the notch at the top of the chip, and to the left of that notch is pin 1, and if you were to count all the way around down to here, that'd be pin 20, and then it goes over to the opposite side of the chip, and that'd be pin 21. If we come all the way back up here, that final pin is pin 40. And what we should see here is 5 volts. So once again, I'm going to put the negative probe on just this metal part down here, which is ground, and the positive probe on pin 40 of the CPU, and we see 5.05 volts. Now that means the CPU is not currently held in reset, so it should be trying to execute code right now, but obviously whatever it's trying to do isn't producing a basic screen for us. Let me just swap this over to a clip, something like that, just so I've got a free hand. So we'll connect that to ground again, and if we power off the machine, check pin 40, so you can see it's at 0 volts, and you should notice when I power this on, it won't immediately jump up to 5 volts. It should take maybe half a second to get there, like that. So that tells me that the reset circuit is working correctly. If it went straight to 5 volts the moment I flick the power switch, then it may be that the CPU is coming out of reset before everything else is ready to rock and roll, and that could certainly cause problems. But just from what we're seeing with the multimeter, that seems pretty normal. In comparison, if we just look at 5 volts over on the user port, as soon as I flick the switch, it's 5 volts, almost immediately. On the CPU, slight delay. So that's probably about as far as the multimeter can take us, but we are lucky in that a lot of these chips are in sockets, and some of these you can actually remove and the machine will still boot at least into the blue basic screen. The idea is that it's possible one of these is preventing the machine from booting correctly, and that's why we're getting a black screen. So if we remove it, we may actually get a blue screen, and we'll know for sure that whatever chip we took out is faulty. There is also a downside of having everything in a socket, and that is the contacts in the socket itself and the pins on the IC can get a little bit corroded, or some dirt buildup can happen in there, and they start making poor contact. Similar to how our switch was working. So what I'm going to do is actually remove all these chips that are in the socket, spray some contact cleaner in the socket itself, and then reinsert them all, and we'll see if that makes any difference. So for this, I'm going to use a little hook tool because I can actually get in under the chip, in between the chip and the socket, and basically gently lever it up a little bit. You don't want to lever it up all the way, otherwise you'll bend the legs on the opposite side. So lever it up on one side a little bit, and then do the same on the other side. It's a good idea just to hold the chip fairly firmly, just so it doesn't try and fly out of the board. And once again, you end up bending a bunch of legs, but if you're gentle enough with it and take your time, it should come out cleanly with no bent legs. I'm going to do the same for the rest. Obviously, if you take all of these out at the same time, make sure you note which position they go back in. Right, so that's all of our chips out of the socket. I'm just going to spray a bit of contact cleaner into all these sockets. You can be a little bit messy, it won't hurt anything. Now on some boards, all of the major chips will actually be soldered directly to the board, so they won't be in all these sockets, and that does make troubleshooting a bit more difficult. But I found with a lot of earlier board revisions, Commodore used a lot more sockets, potentially because they weren't sure how long these chips would actually work for, and therefore putting sockets in actually made repairs easier. Obviously sockets are 1 cent more expensive, so they didn't want to do that with every board, but the earlier boards tend to have more socketed chips. So let's get these back in, and while I do this, I'm just going to check and make sure all the legs are straight and there's not any horrible corrosion on any of them, and then make sure all of the pins are going into the socket and push down from both sides. Make sure obviously you get the alignment correct as well, so remember that notch should be facing towards the back of the machine on all these chips, but the legs on all of these so far look pretty damn good. Right, all our chips are back in the board. Like I said, you want to make sure that they're all in the right orientation and also in the correct position, and that none of the legs are bent out or hanging out of the sockets. Everything looks good. I don't think this is going to work, but we may have just had a poor contact on one of these chips in one of the sockets, and maybe that was enough to cause a black screen. Let's see. No. Right, so like I said, we can remove some of these chips and potentially have the machine still boot. The first one to go for is the SID, the 6581, which you'll find at U18. This is not required for the machine to boot. You just won't have any sound output if you try and play a game or whatever. But if this is somehow faulty, it could be crashing the machine before we get to the basic screen, so it's worth a shot. No difference. Okay, the next two I'm going to go for are these CIAs, or complex interface adapters, at U1 and U2. These basically handle the I/O stuff, so keyboard input, stuff from the user port, serial port, the tape port, and yes, you can remove both of these, at least on a long board revision, and the machine will still boot. You just won't have a cursor or be able to type anything or use the disk drive or the cassette deck or anything. But if they're faulty, you may get a blue screen after removing them. And there it is. So yeah, like I said, there's no flashing cursor, but there is our basic screen. So one of these CIAs is faulty. That's kind of lucky because, well, lucky they were in sockets. These do fail fairly often because a lot of the pins on these chips are directly exposed to some of these ports. So once again, if you have a little bit of buildup of static electricity and you say accidentally touch the joystick port pins, or maybe the tape port or the user port, you can actually end up sending that static charge directly into this chip and frying something on the inside. So yeah, these do fail fairly often, and I think it's usually from, well, static discharge. So be wary of that. The question is, which one has actually failed? I guess we'll throw this one back in. And if it's working, we should get, obviously, our blue screen and also a flashing cursor. If it's not working, we'll probably just get a black screen. And we just get a black screen. Chips can also get quite warm if they have like an internal short, so it is also possible to judge which chip may be bad just by putting your finger on top of it. Obviously you want to have the machine running for a couple of minutes before you actually go feeling around, but if you find a chip that's really hot, like usually burn your finger hot, there's a good chance it's gone bad. That's not always a, surefire indication of a bad chip. For example, the VIC-2 here does get quite hot just on its own during normal operation, but it shouldn't get so hot that it's like insta-burn. And yeah, even though this chip is definitely faulty and causing our black screen, it's cold to the touch. So like I said, not every bad chip is going to be burn your finger hot. Sometimes you get lucky and it's obvious. Other times, like this one, not so much. Right. Let's throw this one in, which should be working. Yep, and there's our flashing cursor. So bad CIA, and unfortunately, these are not cheap to replace either. Now we did get lucky that both of these were actually in sockets and we could easily remove them, but if they were soldered into the board, things might be a little bit trickier. In that case, you definitely want to look into getting either a dead test cart or even better yet, the Des Test Max cartridge by Matthew Desmond. These are both diagnostic cartridges. They may not look exactly like this. This particular one here has the original Commodore Dead Test. These are probably the first things technicians would have used if they were getting a black screen issue like we saw here, because if we insert one of these cartridges with the dead test on it, there is a chance that we may actually get some diagnostic information. You do have to give these about 15 seconds to actually bring something up on screen, if the computer is working enough so that it can actually display something, which in this case is not happening. So that CIA is obviously producing a major fault and probably crashing the buses, and yeah, we can't even boot into the dead test. Let's try Matt Desmond's Des Test switch, because this may actually give us some useful information. Oh no, also a black screen. Okay, well, neither of these diagnostic cartridges would actually help us in this case. Dare I say, if that wasn't in a socket, it would be pretty hard to diagnose. You'd definitely need an oscilloscope to work it out. I think even then, it would probably be pretty tricky. Let's see if we can figure it out. I know I said I want to keep this video very beginner friendly, but I am really curious to see with an oscilloscope if we can spot the fault with this CIA. If this stuff means nothing to you, then don't worry, you can safely ignore whatever I'm about to do here. Well, it's definitely running. Doesn't look too bad. Oh, that's a problem. So it's only getting up to about 2.5 volts. Yeah. That might be okay. That's also a problem. That's a problem. That's probably a problem. That's a problem. That's okay. That's a problem. Wow. So 26, maybe 27, 28, 29, 30, 31. 32 looks a little bit iffy. 33. So pins 26 to 33 all look a little bit iffy, and that's the data bus, D0 to D7. So yeah, that would have been really hard to figure out if this thing wasn't in the socket, because practically everything else on this machine is also connected to those same data bus lines. So yeah, glad this thing was in a socket, because there could have been a lot of chip swapping going on if it wasn't, or at least chip desoldering. Right, so let's get this 6526 out and stick in a known working one. And while we're at it, we'll give these edge connectors a bit of a clean, because they are quite filthy. So again, I'm just using a little bit of isopropyl alcohol on a cotton bud. And after going over both those connectors with just some isopropyl alcohol, you can see the user port looks a lot better. The tape port, not so much, but I think this is more just wear from plugging in and out the cassette deck. So that could still cause some issues, so we'll step it up a notch and use a pencil eraser and basically just rub over these contacts. Sometimes this is enough to get them nice and shiny. Depends on how worn they are. Yeah, maybe slightly better, but there's definitely still some obvious wear on those contacts. So this is probably good enough to avoid any connection issues, but I will demonstrate what the fiberglass pen can do with these things, because this should shine it up even further. The risk with using this is you start taking off the actual gold-plated coating, so you want to go very gentle if you're going this far. So hopefully you can see how much shinier that is to the user port, but yeah, definitely the tape port has had a lot of wear on it, and there's not much we can do about this pitting. The final thing you can do is go over it with a light coating of solder, basically apply solder to all these and then wick it back off. But I wouldn't recommend going that far. That is very much a last ditch attempt, and generally it's not going to be worth it. I reckon this will work just fine. I've heard a melamine sponge or a magic eraser can also help remove some of the oxidation off these, but I don't know where I've put mine, so this will have to do. The underside shouldn't be anywhere near as bad because, well, basically all the crap is landing on the top side. So yeah, as you can see, it doesn't look anywhere near as bad as what the top side did, but we'll still give this just going over with some IPA. I think that should be enough to clean these up. While we're at it, we'll throw some contact cleaner in these ports. I'm just going to spray a bunch in all of them. Not going to bother about the RF connection because I'm never going to use that. Get some in the cartridge port. And of course, our joystick ports. Oh yes, and I don't know what that is, but it needs to come out. It's just a bit of fluff or whatever. Get some in there as well. And that should be hopefully everything working, but we're not really going to know until we run some diagnostic tests. Now, this is probably going to require a diagnostic harness. I'll leave links below where you can find these, but I've got one on hand somewhere around here. Here we go, they look something like this. This particular version is by the great Sven Peterson, who has made a lot of neat things for different computers, especially Commodore systems over the years. I'll link to his GitHub page in the video description as well. So all we need to do is plug all these things into their designated connectors. And the good thing about using these harnesses is you can basically test every port all at once, and it only takes a couple of minutes to do. Whereas if you were trying to test all these ports individually, you'd need, you know, a tape deck, a disk drive or something to plug in the serial port. You'd need to go through the keyboard and test all the keys, although we'll still need to do that either way, but at least this will confirm if everything on the keyboard connector itself is working properly. And of course, this also tests the joystick ports and the user port. You will also need the diagnostic test ROM. I've got a version of it on this cartridge here, which also has the dead test on it. I bought this thing many years ago when I first started out, so I don't actually remember where this came from or if you can still get it. But an alternative would be something like the Kung Fu Flash cartridge, which is very popular these days. It's basically a multi-cart that can run all kinds of different ROM images and programs, and obviously also plugs into the cartridge port. So we'll plug this one in and see what we get. And it's already crashed. Normally things should be happening on screen, but it is frozen, and it says all of our RAM, which is the U9 to U24, or at least most of our RAM, is bad. Let's go back to the Des Test Switch cartridge, because we may have a RAM fault potentially, and this should hopefully tell us if we do. I'll leave the rest of the harness plugged in. It doesn't matter if this is still connected. It shouldn't cause any issues. All right, so it has booted and it's already running the RAM tests. If the RAM had some major fault, then it wouldn't even get this far. So those green numbers from 0 to 7 are basically our RAM. Ew. And it just crashed. Let's just reset it. So yeah, it is making it some way through these tests. And if one of these were definitely bad, I don't even think it'd make it this far. So I don't think it's a RAM issue, which are these 8 chips down here. This could be something else. It could still be a connection issue. What I'm going to do is just sort of twist the board a little bit. See if that forces it to crash. I'm not putting too much force on this. I don't want to snap the board or anything, but if, say, one of these wasn't seated properly in a socket, then that could cause issues, but twisting the board doesn't seem to make any difference. So I don't think it's a bad connection anywhere. All right, let's remove the harness again. Looks like we're still not quite far enough to call this good. Okay, me from the future needs to jump in here, because what I actually found was there was an issue with both of these cartridges. The diagnostic cartridge, which, like I said, I don't remember where I got it from, this was causing the diagnostic test to immediately crash, and it seems like there's just a compatibility issue between this particular cartridge and the PLA that was installed in this Commodore 64. So I had to cut out a whole bunch of stuff from this video because I went chasing my tail, swapping out the PLA, thinking the old one was bad when it was actually this cartridge that was causing the problem. So there will be some slight continuity errors in this video after this, but like I said, I want to keep this as beginner friendly as possible, and watching me go around in circles is just going to confuse people even more. A similar thing happened with the Des Test Max Switch cartridge. This is actually a version that Matthew Desmond sent me before the final version of this cartridge. So it looks a little bit different to the one that you see on his website, but this also turned out to cause compatibility issues with the VIC-2 that was in this Commodore 64. So once again, there was a lot of confusion with me taking out the VIC-2 and thinking it was bad. So you might catch glimpses of an X on the VIC-2 and also on the PLA in this video, but you can totally ignore that. Once again, I cut all that out because I was just going around in circles. Thankfully, there is a pretty simple solution to this, which is to do with a capacitor that actually made it onto the final version of this board. You'll notice in the instructions for these boards, there's a part labeled Mark's Magic capacitor, and the recommended values for that capacitor are 100 to, I think, 330 picofarads. But what I actually found was using a 1 nanofarad capacitor, or 1000 picofarads, sorted out all the issues that I was having with the VIC-2 and this particular machine. So I have obviously passed that info on to Matt Desmond, and you may also spot later in this video that I actually have a new version of the Max Switch cartridge. Once again, this is just a test version that Matthew Desmond sent me for testing purposes, so it isn't officially released yet. But this cartridge worked fine without any extra capacitors needing to be thrown in. Like I said, I've cut a lot of this stuff out of the video because I don't want to confuse people, and hopefully this won't cause too much more confusion, but if you see different PLAs and VIC2s appearing and disappearing from this board, you'll know the reason why. You can safely ignore all of that. Let's just try a different power supply just in case, but yeah, I can't see how this would be causing an issue, but I've been surprised by stuff in the past. Now I can still see, even with that blown out screen, there's still issues there. Sometimes when you get, known characters, like in the top left where it would normally say C64, it currently says Q64. Sometimes that's a clue as to a potential failure. So imagine if the machine goes to read the RAM and there's a C located in there, and it reads back a Q instead. That can sometimes point you to one of the data bits being bad or the data lines. But because this is changing so randomly and it's not always a C turning into a Q, sometimes it's a inverted percent sign, that's not really going to help us on this one. Yeah, it seems to be pretty random. Okay, I think it's time to do another close inspection of this board. Maybe one of these traces has been eaten away from all the crap that's been sitting on top of them. Perhaps we've got a bad trace. Like I said, if they turn sort of a dark color like you see on this edge here, that's usually a sign that the actual copper underneath has started to corrode, because stuff can make it under the green solder mask actually start to corrode the copper. So if we reveal that, it actually looks fairly copper colored. This area doesn't make a difference. This is just like a big ground plane that goes back underneath these ports and basically runs around the entire board. So I was just going to use that as an example, but the copper under there actually looks to be still okay. Yeah, but that is not going to cause any problems. If that was happening on one of these tiny little traces running across the board, then that could be an issue. So like I said, these little dark spots can indicate the copper is corroding underneath the solder mask, and there are a bunch of these little dark spots across these small traces here. The solder joints on the legs of this capacitor also don't look very good, so I think there's two possibilities. This cap has leaked and therefore has started eating all the stuff around it, or what I think is more likely is that it's just from dirt and grime getting in through the case and landing on this board here and basically settling on top of the traces. I don't think there's anything wrong with this cap, but I certainly am concerned about some of these fine traces. So let's see if we can test them in continuity mode with the multimeter. I think they're going to test okay, but like I said, the multimeter is only putting a very tiny amount of current through them, and just like with the switch, if we try and put more current through them, that's when things could start to fail. We'll start with this chunky one back here, which I think is going to be fine. But these slightly thinner ones may have problems. Those three traces also test fine with the multimeter, but like I said, this is not a thorough test of how much current they can actually carry. Generally, with the signals that are running around on this board, the traces don't need to be very thick, so even if they're not 100%, they're probably unlikely to cause our problems, but it's worth checking. We may as well remove this capacitor just so we can get a better look at this area. And yeah, still doesn't look great around there, but I don't think it was caused by this cap. And it's actually a Panasonic cap as well, so usually pretty reliable. We'll use an LCR meter so we can quickly test this cap, but don't worry if you don't have one of these on hand. Like I said, we're trying to do everything with the multimeter. This is more just out of curiosity. and we're reading 9.2 microfarads. This is a 10 microfarad cap, and these generally have a 20% tolerance. So even if it was down to, close to 8 or up close to 12, it would probably still be considered okay. Now, I do see that the ESR, which is the equivalent series resistance of this capacitor, is at 122 ohms, which does seem a bit high. Now, I'm not going to try and explain ESR because it does vary a lot depending on the capacitance and the voltage rating and a whole number of other factors. But generally, I'd expect something like this particular capacitor to have an ESR of around maybe 20 ohms, if that. So if we're seeing 120, then it's at least worth replacing this one. Let's compare that to a brand new capacitor. This is also a 10 microfarad, 25 volt. As you can see, it is quite a bit smaller, but has the same specs. And if we look here, yeah, 10.3 microfarads, so a lot closer to 10. And the ESR is currently 7.9 ohms. That's more like what I'd expect to see. So even though this cap tests bad, I don't think replacing it is going to make any difference. However, I am happy to be proven wrong. All right, let's give this another test. I really don't think replacing this cap is going to make any difference, but I am happy to find another faulty cap that isn't inside the VIC2 can. So there we go. They do exist. But yeah, I don't think this is going to make any difference because that capacitor looks to be sitting between the 5 volt rail and ground, just basically offering a little bit more power filtering. And that's pretty much what all these other electrolytic capacitors are doing. I can almost guarantee that if you took all of these out of the board, the system would probably still work just fine. But with every change you make, it's always worth checking to see the result. Yeah, it's still doing silly shit. All right, well, let's have a look at these traces, as maybe one of them is compromised and isn't letting a signal through properly. But as they're quite tightly spaced together, I don't think it's worth trying to reveal all three of them and touching them up with solder, because then we could end up with solder bridges. And like I said, I'm trying to keep this as beginner friendly as possible. So advanced soldering, or at least intermediate soldering, is something we're trying to avoid in this video. So what we might do instead is have a look online and see if we can work out what signals are on these traces, and see if one of them being compromised matches up with the fault that we're seeing. So rather than trying to figure these out using the multimeter and the schematics, we're instead going to try and rely on BWAC's replica for this particular board revision. He's made a few replicas of different C64 boards, and the neat thing about what he's done is there's actually an interactive bill of materials. And if we have a look on here, you can see all these traces on the left hand side and basically a map of where they all end up on the right hand side. So this is our capacitor here that was having issues, and these are the three traces. Oh, there's actually a fourth trace. Yes, there is a fourth trace just above that capacitor as well, which also doesn't look very good. So let's just click on one of these. So you can see it tells us that this trace is for a clock signal. I think this is just going, yeah, it's just going over to the serial port. You can see pin 4 in red here, and that looks like where it terminates. So even if this trace was broken, say along here somewhere, because we're not actually relying on the serial port just yet, I mean, we'll get to that when we get to the diagnostic tests, but this wouldn't be causing an issue, or at least not the issue that we're seeing. So even if that trace is bad, that's not really going to cause this problem. The next one down also ends up at the serial port, and so does this one. So yeah, those three traces we don't really need to worry about, at least not at this stage. This last one here is address line 6. This could certainly cause a problem depending on where it's going. Because yeah, as you can see, this sort of goes all over the board, but it looks like this particular part of the trace goes underneath our RF modulator, and yeah, it's going over to the cartridge port. That could certainly cause an issue if it's broken somewhere along here. Okay, I think what we're going to do, rather than trying to reveal the copper and touch it up with some solder, we're just going to bypass that little section of trace with a little bit of wire. That'll be less permanent and yeah, a lot easier to do for beginners. So it's just a random bit of wire, probably from a ribbon cable, like an IDE cable or something like that. So it's fairly thin, but yeah, this should do the job just fine. So if we take a look at this trace, which goes up behind these capacitors, eventually ends up right at this point between the RF modulator and our video connector. I'm just going to try and get a little bit of fresh solder on there. And on the other end, it ends up right here. I'll throw a little bit of solder on there. And while we're at it, a little bit of solder on our bare wires here. And normally you'd want to use flux to get a good joint, but this will do for now. It's only a temporary thing. So that's soldered on that end, and I'll just cut this back a little bit. Doesn't have to be perfect. Stick a bit of solder on there. And just tack that on the other end. Just like that. Doesn't have to be pretty, it's just bypassing that trace temporarily. Okay, let's see if that makes any difference. Video is being stupid, but yeah, I can already tell C64 diagnostic. I don't think so. Well, it's worth a shot. I think we can safely remove this. I don't think it's making any real difference. I'm sure that trace is probably fine. So let's have a look at the C64 pictorial fault guide. This is just a collection of images, basically with different faults and the chips that could potentially relate to whatever fault you're seeing on screen. So see if we can spot something that you know, is a close match. Ooh, U14. Kinda. There are some definite random characters happening there, so U14, one to keep an eye on. Let's just go through the rest. U17, our PLA. This can cause all kinds of crazy issues. You never know what you're going to get with a PLA, like a box of chocolates. SID, there's no SID installed. U25 logic, sorta. U26 logic, ooh, once again, yeah, those spurious characters. U27, funny colors. Crystal oscillator, I'm certain that our clock circuit is now working perfectly fine. And that's about it. Capacitors, traces, well, yeah, so you can see what happens when you might have a broken trace, but, well, could still be a problem. But I definitely think we should check out U26. What was the other one? I think it's U14. That's U14 right there. And I can say the actual legs on that chip do look pretty tarnished. I don't know. It seems to just happen with certain chips. The legs just sort of tarnish over time. U26 is this one right next to it. And yeah, given this one's a bit tarnished, I wonder if that's the problem. Because yeah, I really doubt it's the sockets at this point. I think we've cleared them out and stuck chips in and out of them more than enough. Ooh. Did I just... Oh. Is that... I touched something around here. I think it's one of the legs on the PLA. Yeah, that shouldn't be happening. It's just around pin 4 or 5, it seems. Like, if I twist this thing, it doesn't do anything. It's only when I actually touch on those pins. Alright, pin 4 or 5 of the PLA, A13, A14, A15, VA14. So that is one of the VIC address lines, hence the V. They do seem a bit suspect because we're seeing sort of video fault, but the machine is seemingly otherwise running, and it passed all the diagnostics from Des test switch. So, oh, and it does end up at pin 2 of U14, which is the one that we were looking at. So it's more like a display fault. The VIC2 is just grabbing, you know, random garbage from somewhere. It's not actually crashing the machine though, it seems. So pin 2 of this thing, if we, yep, if we touch right around there, it's the same thing. And touching anywhere else on the board or any of the other chips doesn't cause any issues, which is what you'd normally expect. Yep, it is literally only that pin, which is connected to the PLA on this pin. That's a problem. Okay, so because I need to know, we're going to have a look with the oscilloscope again. I don't think this is really necessary. I'm pretty certain this chip is bad. Let's see. Oh yeah, that definitely shouldn't be sitting around 1.5 volts. It should be around ground or at 5 volts or at least 4 volts and maybe rapidly changing between those two. Definitely should not be in the middle. Yeah, same at the PLA. Huh. Even just touching it with the scope probe is enough to make weird shit happen. Alright, we got to get it out. I suppose we should quickly check the schematics, make sure it doesn't go anywhere else. So here's the PLA. VA14, pin 5. So it goes over here. So this means it goes to the previous page, but it also comes up here somewhere and then around here. Ends up at, oh yeah, that's U14, that's what we were just looking at. On the other page, there it is in there, VA14 goes to pin 2 of U2, one of the 6526s. Well, that's not installed at the moment, so it obviously can't be that. And that looks like the only places where that signal appears. So definitely got to be U14. I'm pretty damn confident, and you always want to be fairly confident before you go trying to remove these chips, because like I said, it's not as straightforward as it looks. So first thing we're going to do is put some fresh solder on all of these legs. And while you're doing this, you can give these pins a little nudge. If they move about, it means the solder is molten all the way through to the other side, which is what you want to see. And some of these pins do end up a bit bent over during the manufacturing process, so this is a good opportunity to straighten them up. Now, is it possible to do this just using braid? Probably. It's going to be very difficult and not really something I'd recommend. For getting something like this out, I'd probably at least want to use a solder sucker like this one, or better yet, an actual desoldering gun like this thing. Another option is to use a hot air station like this one, but once again, that's more tools, which means more money, but they can really help get very stubborn chips out of boards, because you can basically heat up the entire area and then really focus a bit of that heat around the chip itself, and that should melt all the solder at the same time and allow you to pull the chip out. Then you can clean up the holes using a bit of braid or a manual pump. I'm going to come in with the manual pump, see how this goes. So I'm going to heat for a couple of seconds, get the nozzle right over there, and push the trigger, rinse and repeat. One of the things I really like about this sucker is it's got like a silicon tip on the end here, so it's fairly heat resistant, which means you can heat the joint and keep your soldering iron there so you're still pumping heat into that solder. Get the tip right over the top with the soldering iron still in place and pull the trigger. All right, now I'm going to come in with a little bit of braid just to get any remaining solder off that joint, although it looks pretty clean as it is. But we want to give ourselves the best possible chance of getting this chip out without doing any damage. All right, and looking at it from this side at least, I can't see any leftover solder. You want to make sure that you get rid of any solder that's in there, because even if the tiniest bit is hanging onto one of those legs, when you go to remove the chip, it's going to take whatever trace is connected to that leg with the chip. And then you've got a much bigger repair job on your hands. So you can take as long as you need to with this kind of thing. You definitely don't want to rush it, especially if you're inexperienced. So we'll check this from the top side as well, because there's a good chance that even if you clear out the solder from the bottom side, there's still going to be stuff left behind on the top side. So I'm just going to come in and sort of gently push these legs with the soldering iron in towards the chip as I go along. Definitely on this side of the chip, we've still got quite a bit of solder. You can see how much is coming up in my braid here. So, like I said, this isn't the ideal way to remove these things, but if you've only got basic tools on hand, you might not have any other option. I just realized what I did. I desoldered half of the chip next to it. That's why there's so much solder on these legs, because I haven't even removed the solder yet. Yeah, you can see this is the other side of that chip because I've already started removing some of the solder by sucking it back through to the top side. That is why you should always double, triple check and also mark exactly the thing that you're going to solder. I got a little bit carried away. That's fine. We will go back through these and try again. Another thing that can help is actually adding some extra flux to the joint. I'm not going to do that in this one because, once again, you probably don't have flux on hand. And this particular braid actually has quite a bit of flux already impregnated in it. So as long as you're basically, cutting the used parts off and using a fresh bit every time, or at least almost every time, you shouldn't really need to add extra flux using this particular braid. But like solder itself, not all braids are equal. Alright, well, I can no longer see any obvious solder holding this thing in. What I'm going to do before I try and lift it out, though, is just give these legs a little bit of a tweak with some tweezers. You can usually feel if one of them's stuck. They should move fairly freely, so just rock them back and forth. That feels fine. Seems okay. Not sure. They do feel somewhat loose, but the chip's not falling out on its own, so something's holding it back. I have found sometimes that the chips just seem to be really pressed hard into the board, so they won't budge without a little bit of encouragement, but it is risky trying to pull them out if they're not freely moving. I'm just going to give it a bit of a tweak. Yeah, I think that is now jiggling about. I'm pretty sure that's free. There we go. I did manage to get all the solder out of those holes and off these legs by the looks of it, which is why the chip actually came out without lifting any traces. But like I said, you always want to take as much time as you need doing these things, because once you pull out a trace, it's a little bit more difficult to repair, especially if you don't have the skills. So now that we've got this out, I'm actually going to put a socket in and then install a replacement. As to where you can find a lot of these logic chips, eBay, AliExpress, you might get lucky with. There are also fake chips out there, so they're basically being sanded down and remarked. So yeah, your mileage may vary when buying on the second-hand market or the AliExpress market. And when it comes to sockets, I do keep quite a selection. These ones would have come from AliExpress and I haven't had any issues with them. So when it comes to sockets, AliExpress is fine. I prefer to get these dual wipe sockets. So you can see these have the contact on the outside along with the contact on the inside. And that's unlike a single wipe socket like the ones Commodore used, which only have the contact on the inside. So these are a little bit better at actually making full contact with the chip itself. Some people prefer to use the machined pin sockets, so you can see they've got a tiny little hole, but I actually prefer to use the dual wipe because the legs on these are actually flat, and flat peg in a round hole. Now, of course, when I go to flip the board, that socket's going to try and fall out. Some people like to put a little bit of blue tack or even some tape around just as a temporary measure to hold it in place. I prefer to use the old fingers just to hold it in place and then awkwardly struggle trying to hold the solder in the right spot and the soldering iron and just tack in one side. And then tack in the other. And I can let that socket go and then just reheat these joints just to make sure the socket is seated flush onto the board. And before I go any further, make sure that I actually put it up the right way. So yes, that little cutout is at the top of the socket where it should be. Didn't screw up this time, but let's just say I've installed one or two of these in the past backwards and only realized after soldering all the pins, and at that point it wasn't really worth trying to take it back out. So here's our replacement, and yeah, as you can see, they do look slightly different, but they are basically the same chip. With this 74 series logic, you want to make sure that the letters in between the numbers are the same on both chips. So you can see they're both 74 LS 258. The letters at the end don't really matter. I wouldn't pay too much attention to those. I think this one, yeah, that'll go in. Yeah. Well, I don't see any random characters. Let's give this a fingering. Yeah, okay, it's working. We really need to hook up the diagnostic harness because once it goes to test all these ports, that's all going to fail. We need to put all this stuff back in first. And while I'm at it, take my good chips back because I need to put them back in my other Commodore. I'm pretty certain at this point all the other chips that we have for this board are all working correctly. Don't know about the SID, we're about to find out about that. This video thing is really annoying me. It looks like shit and it always comes up super bright. Very annoying. So far, so good. Everything is looking okay. Let's... I do hear the SID. Volume's turned down. Alright, I think that actually sounded okay, which I was half expecting the SID to be bad as well, especially these older ones. This one's from, wow, the 22nd week of 82. I don't even think the Commodore 64 was on sale back then. Pretty sure it wasn't. I'm pretty sure it came out in like August. So that's like a, you know, that's a very early SID. And I'm surprised it still sounds okay. But the diagnostic test there only tests some basic functions of the SID. So let's put a keyboard back on this thing. We'll give that a test while we're at it. And properly test out this SID to make sure it's fully working. Because, yeah, the diagnostic test isn't a true test of all the voices and filters and all those kind of things on the SID. I'd be very surprised if all of the keys on this keyboard work. With the power LED, as you can see, there's only 2 wires and there's 3 pins here. Doesn't really matter which way around you plug this in, as long as it's not overhanging the edge of the connector. The center pin is ground and the 2 outer pins are both 5 volts. So either way around you plug this in, it'll do the same thing. So I'm going to use my Easy Flash 3 cartridge. This is kind of similar to the Kung Fu Flash, I guess. This one has some advanced features that the Kung Fu Flash can't do, and the Kung Fu Flash can do some things that this cart can't do. So if I was buying a new multi-cart today, I'd definitely consider the Kung Fu Flash first. And if you really want to get kind of crazy with Commodore 64 stuff, maybe look into the Easy Flash 3. Oh, and keyboard doesn't work at all. Let's just pull that out for a second. Wow, not a single... Oh, U works, if you're lucky. G and F also work, maybe. UGF. Oof. Okay, so like I mentioned, the keyboards between these machines are interchangeable, so let's borrow this one, which may have originally been on this machine. I don't actually know. I'm just going to sort of sit it like that. That'll do. Okay, this sort of works, mostly. Let's plug this back in and we can give the keyboard and the SID a proper test, hopefully. Do the keyboard test first. Obviously this corner key is not going to work very well. It might still, it still registers even though the key's not there. Yeah, there's definitely a few keys that are hard to register. They need a few goes. Yeah, not great. F1 and the spacebar don't want to work at all. Let's check the SID, if we can. A little bit scratchy at the end there, but all in all, it seems mostly okay. I wouldn't expect too much from a SID this old. Like I said, I don't think I've ever seen one this old with 22nd week of 82 printed on it, and I'm surprised it still works at all, to be honest. So we now have a fully operational board. The only problem is we don't have a fully operational keyboard to go with it. So I'm going to pull this filthy one out because it's already in part of the bread bin case, and let's see if we can resurrect it. So all these tiny little screws need to come out, and it looks like somebody has replaced a couple of them with random ones. And we also need to desolder these two connections that go to the shift lock key. They're pretty simple, just grab them with some tweezers, and that one wasn't even soldered. This one might be. Just heat up that solder and they should pull out. Now we take out the million screws. I'm not going to bother taking the actual keyboard itself out of the case. If you just take out these screws, you can actually remove the keyboard and have it floating around like this one, but we don't need to go that far. Yeah, that's a lot bigger screw, so I need to make sure I put that one back in the same spot. Okay, hopefully that should have done it. Yep. So there's the back of our keyboard. Once again, it's just another PCB with some gold contacts on it, and the actual keys themselves have these little carbon impregnated rubber things that push down and basically make a connection between the two contacts. Sometimes you'll find that this side also has carbon contacts on it. Depends on the keyboard manufacturer, but these Mitsumi ones, I'm pretty sure all have these gold contacts instead. And just looking at all these solder joints where all our wires come in, they all look okay as well. So yeah, maybe just these carbon contacts are all shot. Unfortunately, that can just sort of happen to these things over time, and there's no real easy way of resurrecting them. Let's give this a clean first, and then if we need to, we'll try and look at some ways that we might be able to get at least most of those keys working again. So this side is pretty simple. We're just going to go over all of these with some isopropyl alcohol. Yeah, not much doing there. I mean, they looked pretty clean, and they are pretty clean. So when it comes to these things, you don't really want to scrub them with IPA because it seems to actually kind of wick the carbon out of the rubber contact itself. So I used to sort of go over them with a light rubbing of IPA, but I don't even do that anymore. What I'm going to try and do is just use a little bit of paper and basically rub the contact on the paper, or the paper on the contact, and see if that brings some of these back to life. So with just a bit of paper, I'm just going to push the key in that I want to clean up, and if we rub that over there a little bit, it should sort of take off a layer from the top, just like that. Keep doing that until you've done all the keys, put it all back together, and see how lucky you get. All right, that is all of our keys done. Like I said, I used to use a little bit of isopropyl alcohol to do this, but I found that over time the keys stopped working again, and it seems they're never really the same afterwards. So I've actually found this paper method seems to get most of them working, if not all of them, and they seem to continue working afterwards, as long as you don't store them outside or whatever. Of course, we're going to have to put a bunch of screws in. I won't put all of them in, but at least enough to sort of hold everything in place. So we're no doubt going to be opening this up a couple of times. All right, that'll do. Not going to worry about the shift lock key because, yeah, like I said, we're probably going to be getting back in here very soon. Let's plug in the power LED. Got to have a power LED. How else will you know if it's on? Oh, we got one. We got two. We got three. Well, we got five. Okay. It's looking pretty good. Let's bring up this keyboard test. Did I manage to get all of them working in one shot? The restore key is a bit of a quirk, especially on the longboards. You actually have to give it a good shot to actually register. I believe Commodore did that intentionally, and I just tried to use the shift lock key, which isn't connected. Just so, well, I guess if people accidentally bumped the restore key, they wouldn't lose whatever they were working on, or something like that. I don't know. But yeah, you do, if you just push it normally, it probably won't register. You actually have to give it a bit of that. And I'm not doing anything special to these keys, I'm just touching them as you would normally type on them with one finger. But as you can see, every single one works. Oh, it's magic. Alright, and I'm going to solder that before I forget, because I always forget. Seeing as we fixed this thing, it's only right that we put all the screws back in. Let's see what we've got here. Looks pretty close to the originals. What are we missing? One there. That one's had a big screw in it. That one's had a big screw in it. Well, we can at least use something a little less ugly, I think. Maybe one of these. Yeah, that's going to confuse the next person. Good as new. Give it a fresh bit of tape even. There we go. It's like brand new windshield wipers for a busted windshield. Well, I suppose if this board is now fully working, we should really pull apart this switch and clean it out properly. We've already desoldered a chip, so the hardest part that I wanted to show in this video has pretty much already been shown. The switch should be a piece of cake. And there's also these two up here. That's not the right screw for the bracket. And that mostly worked. I think the rest can be done with braid. It's just a tiny little bit here and there that's going to cause problems. There it goes. Alright, to open one of these bad boys, we need to bend out these little tabs on either side. So I use my hook tool, but obviously don't put my fingers in front of it because that will happen and I'll slip off and stab myself. Flathead screwdriver probably would have been a better choice. That's bent out enough. And once you open these, all the little insides will fall out all over the place. Need to bend this out a little bit more. Ah, they stayed in there. Probably because they're stuck in with all that gunk and crap that's in there. So there's a couple of little contacts. Where'd that go? So there's one of our contacts, and the other one. Get out of there. So once again, bit of a clean with IPA, and oh, look at that. Beautiful. Not so bad after all. Just to be sure, we'll give it a little bit of the old fiberglass pen. And we're not done there because there's also contacts on this part of the switch as well. So once again, IPA and a bit of a zhuzhin with the fiberglass pen, and we should be good. Those ones down the bottom are really dirty. You can hardly see them. Try and get all that random stray fiberglass bits out of there. And not into my fingers, preferably. It's probably going to be hard to tell, but there is just a slight bend on either end of these. So when you put them back in, you want to have that slight bend facing up out of the switch. Right, now the fun part is getting this back on without these contacts falling back out. So this thing here is basically what pushes down on these contacts. So you can see there's sort of two nipply bits either side. We need to make sure they sit flush over those contacts. And also while you're doing this, make sure the little tabs here are pointing the same direction as the all the other things, because I can't tell you how many times I've gotten one of these back together and then realized I put this part upside down and these were pointing upwards. That feels pretty good. Let's bend these tabs back down. Use the old multi-grips just so I can get some fairly even pressure on either side, and you don't want to squeeze too hard, otherwise you'll crack the switch housing and then you'll be fucked. That'll do. Alright, that switch should now last for donkey's years. Maybe. Get this bracket back on. And finally, we can screw this thing back in. I'm not going to be cleaning up the case. I don't even want to get started on that. So there's easily another hour's work in getting this case cleaned up, popping off all these keys and cleaning underneath, because no doubt it's pretty filthy under there as well. But everything currently works, so I'm finally happy to call this machine good. Just needs a clean. And one of my RF modulator replacements to fix up that terrible video. And maybe some of my replacement ROMs too. And maybe some heat sinks on all these chips. Yeah, not far to go. All right, bread bin number 2. Yes, we are still going. We're going to get all of these done in one video. So hopefully this one won't take anywhere near as long. I'm obviously not going to try and explain all the things that I've already explained. Here we go, number 2. Let's see what happens. It's another 407. Yay. Oh, it's got a bunch of ceramic RAM. It's proper old school. Right, you can fuck off. I think it's definitely worth taking a peek under here. Please don't be a ceramic Vic 2. Open sesame. No. And those caps have leaked. Ew. Get out of here. But on the bright side, all our major chips are in sockets again. Alright, just for fun, let's try and power this thing on with those bad caps in there. What's a bet that either it's going to be another bad power switch? Oh, it was already powered on. Black screen. Yee-hoo. At least we're getting a video signal, so those caps haven't destroyed anything badly enough that we're not getting a clock. Because we need clock to generate video. But potentially all of this could be broken. We're also getting voltage, so hey, maybe the switch is doing alright on this one. 9.2. Oh. We've got no 5 volts. So half the switch is working. Or something is drawing a lot of current and pulling that voltage rail down. Now everything is stone cold. Okay, well, we've already seen what to do with the switch. We've already seen what to do with these caps, so I'm just going to get those done off camera. Unless something interesting comes along, we'll jump straight to once all that stuff is fixed up, and then probably continue troubleshooting, because I'm almost certain that something else has got to be broken on this. Righty, switch has been removed, cleaned, reassembled and stuck back on, and of course I've replaced these 2 caps. The switch didn't look too bad, and there was definitely a lot less damage around these caps. In fact, all the traces around here look perfectly fine, so there's a lot of perfectly fine in this video, isn't there? I notice I keep saying that. I'm sure some other people have noticed too. Alright, let's see what happens. Still just a black screen. What a shock. Let's check for our voltages just to make sure. So 5 volts should be here now. 4.838, a little bit low. Suppose that's okay. 9.2. So switch seems good. Right, so something else is causing our black screen. Let's start off with the Des Max cartridge. Ooh. Start off with getting some contact cleaner in this joint. Especially in here. And a bit for you, a bit for you, a bit for you, a bit for you. There you go. Oh, I forgot to put the side plate back on. That's alright. We get nothing. You might have noticed the little reset light on the switch cartridge went on and then turned off. So that's a good sign. So Vic2, as we're getting power, it's producing a video signal, but it's just a black screen. Des Max cartridge isn't helping us right now. So we'll start once again with removing the SID, because these are almost always in a socket. So that's always going to be the easiest chip to remove. Probably not going to help. It's worth a shot. Nothing there. Yeah, once again, our CIAs are in sockets, and if yours are not in a socket, well, you're going to have to start learning how to use an oscilloscope. But like I said, I want to try and avoid bringing out too many advanced tools. I bet you it's another bloody CIA. Ooh, no, maybe not. Maybe not. Let's pull the ROMs out. We know we don't need them for the dead test or the des test, seeing as we have the luxury of all these things being in sockets. Maybe. Maybe not. Okay. So we need a VIC2, we need a PLA, and we need a CPU. That's not helping. Do a quick inspection of the board. I probably should have done this before removing all the chips, but just to see if anything jumps out at me. Apart from dust and shit. Nah. And again on the underside, yeah, I don't think any work has been done to this board. Apart from the stuff I did, those two caps and the switch. Something is really preventing it from booting. My money's going to be on the PLA. Good thing we've got a known working machine full of socketed chips that I put the screws back in for no reason. Get out of here, you. No. CPU then. Oh. Did I put that in before? I don't think I did. Of course, we're going to go to black screen without any ROMs and without the dead test or the des test cartridge. Yeah, okay. So it is one of these two, but because I didn't have that cartridge in at the time, I don't know which one. We'll find out soon enough. Be good if I could say something. Okay. That's far enough to know that everything at the moment is probably working as it should. Now, I did suspect the PLA first, so let's stick the old one back in with the cartridge installed. And that's a black screen. We'll put the original CPU back in with a known working PLA. Oh, and that's a black screen. Did I mess up a pin or something? Nah. Oh, both the CPU and PLA were bad. Yeah. Of course, we can verify this with our known working machine, and that's always probably the better way to do it, because if you suspect one chip and you know that all your other chips work, then it's easy to stick one in and leave the rest as is. So that is what I'm going to do. I'm actually even going to take the VIC2 out of this thing, and we are going to go back to the first machine, because clearly haven't seen enough of this guy. Alright, what you need? Crap. Which one of these worked? I think that's the good CPU. So make sure everything works first before we start throwing dodgy chips in it. Potentially dodgy chips. Okay, maybe that's the bad CPU. I hope that's the bad CPU. Oh no. Why am I getting a black screen on this machine now? Working just a minute ago. Because I was rushing things and wasn't paying attention, that pin didn't go back in the socket, it bent out. Okay, that's better. I'm pretty sure this is the bad CPU. I think that pretty much confirms it. Yes. So, first one down. Now, out of curiosity, I do have to know if it's something that would have been obvious with the oscilloscope. I just got to know. So I'm pretty sure it was coming out of reset. We'll be able to see what the reset signal actually looks like on the scope. So when I power this on, you should see a little blip, but then it'll stay low for about half a second after that, and eventually should go straight up to 5 volts. See? So that is what a good looking reset circuit looks like on an oscilloscope. But as we've already seen, you can also test that with a multimeter. All right, pin 1 is our clock into the CPU. It should be 985 kilohertz, which it is. On NTSC, it's 1.02 megahertz, I think. Pin 2 is ready. I'm pretty sure this is coming from the VIC. I've just put the cartridge back in just so I've got access to this reset button, because sometimes it is worth actually attempting to reset the machine just to see if any of these lines change, especially ones that are either stuck high or stuck low. Maybe nothing happens on that line until the machine actually fully initializes, so we might not see much. Pin 3 is IRQ, that's interrupt request, and I'm pretty sure that'll remain stuck high until more things are working. Same goes with NMI, we can't do anything with that at the moment. Pin 5 is AC, that's sort of kind of partially how the VIC2 and CPU share the address bus, so, and yeah, it should look pretty much like that, so that actually looks good. Pin 6 is a VCC, so that's just 5 volts. Pin 7, okay, 7 to 13 is all address lines, so they should look something like this. They should be going all the way down to about 0 volts and coming up to at least 3.5, maybe even all the way up to 5 volts. What you don't want to see is signals that sort of get stuck in between that for a long period of time. So if we go through all these address lines, okay, that's the kind of thing that you don't want to see. Pin 10 is address line 3. And yeah, if that's happening, the machine's never going to work. Not even the dead test or DES test. Yep, that's also a problem. That's a problem. That's a problem. Looks like all the address lines are all kinds of screwy. And I think, ooh, that one looks okay. For whatever reason, address line 10 looks okay. The rest so far all look messed up. And yeah, even the ones on the other side, 14 and 15, are all bad. So if I had have seen that without removing any of these chips, just probing around, especially at the CPU, that would have almost confirmed for certain that the CPU is the fault, because I'm pretty sure it's the only thing that's going to have all of these address lines on it. If it was only, say, address line 0 to address line 7 or something, then it's possible that it could be another chip that's at fault, because chances are some of the other chips are also going to have all of those address lines attached to them. But given that, well, address line 0 all the way up to 15, except for 10 for some reason, are all bad, that pretty much confirms that it can only be the CPU that's the fault. Okay, the other thing we had was the PLA, wasn't it? Let's have a look, make sure the broken one is actually broken. And once again, we'll have a bit of fun with the scope just to see if we can see something obvious that would have pointed us towards the PLA anyway. Ah, this PLA is working. Or is it? Ah, yeah. I don't think there's anything wrong with this PLA. That is fine. God, that video output though. Ugh. It's getting worse, isn't it? probably bad capacitors inside this thing, but I'm not even going to bother trying to open it up because in order to change those caps in there, you need to take this thing off the board. So if I'm going to take it off, I'm going to replace the whole damn thing. Right, we'll leave that PLA in there because apparently that's good. We may as well go through and test all these other chips from our second machine. May as well throw the other SID in as well. Why not? Basically, we've transferred everything from our second machine back to our first machine. Like I said, I'm going to hook up the diagnostic harness to this machine and test the CIAs from here. If it all tests good, then all of this stuff can go back in the other machine, and then I'll do another round of testing to make sure everything works when it's in there. Does thirsty work? I'll recycle that later, I promise. I should clean up this bench while I wait. Dickheads, meet the dickheads. Oh, slightly better. Still disgusting. Oop. It passed. Okay. The basic checksum is a little random thing that happens with this particular DesTest Max cartridge. It is a known issue, so I think it will actually be fixed at some point in the future. In fact, Mr. Matthew Desmond actually sent me a prototype of the new version. I don't know if I'm allowed to show this on camera yet, but there it is. So sorry, Matt. But also thanks, Matt. Yeah, this does seem to fix that minor issue. It only seems to happen with ceramic VIC-2s for some reason. And yeah, just randomly the previous previous DesTest cartridge can sometimes throw a bad basic checksum. Right, quick run of the diagnostic test. This is really just to test that these two CIAs are working properly, and I guess at least the SID might be partially working. Hopefully it's fully working, but 16th week of 83, not a good time for reliable SID chips. Then again, the one from 82 is still working, so if all of this works, then all these chips can go back in the other board, and at least we know from that point, yeah. No sound. Our SID is dead. Oh, and I think I just realized why the video was, well, why the picture was so fuzzy, because that came out a little bit. If we go back to the basic screen, we'll probably be able to see this. So yeah, we're not getting a proper ground connection between these two. Basically, because I've got the audio plugged in, the ground from here is going, well, from the Commodore through this wire over to the RetroTink, but the ground from the video signal is also relying on that same ground from the audio signal. So yeah, that was why it was so fuzzy. It still looks like shit and there's jail bars everywhere, but that explains the random noise in between. Okay, this SID chip is bad. I would pour one out, but I'd rather drink it. Yeah, pins are a bit rough, but they're shiny at the point where it matters, where it actually goes into the socket. I think this will probably pass. The reason it showed controller ports bad with this SID installed is because the SID handles the analog inputs from the control ports, and those were used mostly for those little paddle games where you have that sort of dial that you twist around. What do you mean user port bad? And you one bad. Oh, okay. Probably just a bad connection. Okay, so everything's good now. Good thing I didn't immediately write it off. So we'll borrow the SID and the PLA from our known working machine. And now that we know that all these other chips are working, let's stick them back in the other board and see what happens. Alright, another RAM test, because we don't actually know if all of this RAM is okay. We don't know if any of this stuff over here is okay. So, worth checking. So as you can see, I've left this running for the last, well, at least 12.5 minutes, and everything is working perfect. No issues with the ceramic VIC2. Basic checksum is also okay, so I think this is all pretty good. Only thing we need to test now is the diagnostic harness, which means I should clean up these ports first, and hopefully this machine will be done. Well, except for the keyboard. Right, edge connectors have had a bit of a clean. You can see they are still pretty rough, but if I keep going at them, well, if I keep going at this one, it's going to end up looking like this one. So I think it'll be okay. I reckon that's good enough. I'm not really expecting any issues because, well, we know all these chips are good. What else is there? What could possibly go wrong? That could go wrong. Got to be this edge connector. Could also be my harness because it's probably also dirty on the inside. Bit of contact cleaner for you. And a bit of that, a bit of that, a bit of that, a little bit of that. Oops. Seeing as you asked nicely. A bit for you. There we go, that's looking better. We've got a good SID in there from 82, we know that works fine. Did we already test? We did already test this. And it had a few bad, no. Did it have a few bad keys or a lot of bad keys? The other one had a lot of bad keys. Maybe this one only had a few bad keys. Yeah, this one only had some somewhat iffy keys, but nowhere near as bad as the other one, which we fully resurrected, so I'm sure we can do it with this one as well. Do we need to see that again? Probably not. Might just skip through this part. Alright, keyboard is re-secured, everything is back in place, and I also replaced that plunger because the top of it had broken off, so to replace these you actually need to take the back of the keyboard off, so at least with that done now, if somebody manages to acquire a new key, it'll be a lot easier. Just pop it on and you're done. Let's make sure this entire keyboard actually works. Right, can you believe it? We finally made it to the shortboard. I think this is actually working, but, well, we're going to test it to be 100% sure. So let's plug her in. Yeah, so 8580 SID in these. You cannot put the 6581 in a shortboard. Likewise, you can't put an 8580 in a longboard. And same with the VIC2. They are not interchangeable. The other things are somewhat similar. We've still got two CIAs. This is now our CPU. It's labeled 8500, but you can actually put a 6510 longboard CPU into one of these and vice versa, so that's safe to do. just not the SID and the VIC-2. That's, yeah, those two definitely avoid. You need to do some modifications in order to make that work properly. We're not going to be covering that in this video, that's for sure. This big guy here is our Super PLA, so it combines the original PLA with a bunch of the other sort of, you know, little bits of logic all over the place into one big IC. These two here make up the total 64K of RAM, so they're 64 kilobits times 4 bits wide, so that gives us 64K. That's versus the 8 chips in the long board, which yeah, are only 1 bit wide, so you need 8 of them to make a kilobyte. Here and just hiding under here are our two ROMs. Our character ROM is still the same, but the kernel and basic ROM is now combined in a single IC. And yeah, you can see over this side there's a lot less voltage regulation going on because with the reduced chip count and newer manufacturing process, these run a lot cooler because they're a lot less power hungry. Now, there is a good amount of corrosion over here, but you can see it's on these big thick copper planes, so it's probably not really something to worry about. Maybe I might clean that up a little bit, but I don't think that's going to cause any issues. Similar story over here. There's, you know, a little bit of corrosion, but for the most part it's only in this big copper area. Anyway, let's plug in video, see what this one does. Ooh, that power switch is very, needs a good switching. All right, it works. Yay. Let's see if it really works. Start off with the RAM test. Oh, yeah. The power switch is very firm. Not a bad thing, I guess. I mean, it works. And the video is very blown out. The shortboard RF modulators also suck ass. Again, I'd highly recommend replacing one of these with my RF off, but yeah, if you can deal with that, then go right ahead. And it's actually crashed, hasn't it? Has it crashed? It's not supposed to be stuck like this. Start again. All right, that time it worked. Is it just me tapping on stuff? Oh, yes. See, down the bottom of the screen, bit 5, across from that, it says 0 page and AM. That's not supposed to say that. And that seemed to pop up as soon as I tapped on the board. Let's start again. Yeah. That's a problem. There are very few things in sockets on this board, only the SID, the VIC-2, and this thing here, which is the clock generation circuitry. So this kind of takes over from all that stuff around the VIC-2 on the previous boards, like inside that metal can. Basically all reduced to the crystal and this chip. And they're the only things in sockets, which isn't a big surprise for the shortboard versions. Seeing as tapping on the board definitely made a difference, we're going to take out these socketed chips because it could just be a bad connection to one of these sockets. And I can already tell you right now, well, that's not supposed to be in there. The VIC-2 socket does look a bit crusty on some of the pins. At least they're dual wipe sockets, so, you know, Commodore upgraded. Ooh. Must be all that money they saved from not socketing everything else. They splurged a little. That's a bad socket. Okay, I can see that there are a couple of pins on this socket that do not look great. Mostly this one here and this one over here. Let's get this board out. Alright, let's put this thing where it belongs with the rest. So I'm going to cheat a little bit here and only remove this pin and this pin from the socket. Everything else is staying in place because I don't really want to desolder this whole thing if it's only 2 bad pins. Third pin down on the left. And 1, 2, 3, 4, 5, 6, 7th pin down on the right. Bit of fresh solder on those. Get some braid in there to be sure, Alright, both those pins are loose. Flip to the top side. Find the pin that you want to remove. Jam something down in there, because it's coming out anyway. Make sure you've got spare sockets on hand before you do any of this, of course, because we're going to need to replace these 2 pins from somewhere. Alright, now that I can grab onto that bit, I can finally... Ooh. Would you believe it's still holding on somehow? Let's get some heat into that. There it goes. You bastard. Alright, do the same for the other one. There it goes. Hopefully, we can put some new pins in there without needing to remove this socket. Couple of fresh pins from a sacrificial socket. Are these going to go in neatly? Oh, I can see straight through there, so they should go in. Okay, yeah, that actually worked. I can feel the pin on this side. And it's... I mean, it looks different from the rest, but maybe that's just because it's shinier than the rest. Let's try this one. Which also, yeah, it's not going to drop straight in because there must be just a little bit of solder on the top side that's stopping it. Would I call this basic techniques? Maybe not. Not really advanced techniques either. This is hacky techniques. But you know what? If it works reliably, who cares? Meow, 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 meow. Meow, 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 meow. Meow, 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 meow. How are these microphones still working? They're pretty close to dead. Okay, so I walked away to get myself a little refreshment, and this thing is still going, hasn't failed on anything. Tapping around doesn't seem to bother it. It is still running. This is normal. So no problems with the RAM. We'll quickly give these ports a little clean. They actually look quite good, so just a bit of IPA on these should be enough. Give the other ports a bit of a squirt with contact cleaner, and with any luck, it'll pass the rest of the tests with the diagnostic harness. See? You know what I am seeing? Those counters, the AM and PM timers, are stuck at 0. That's not a good sign. Yeah. Kind of expected those ports to return bad. And we've got no sound. We should have sound. That is not good. I wasn't even looking at those timers on the other tests. That's because you can hardly read them. No, they're stuck at 0. The reason they're not turning red is because it only checks if they're both the same, and, well, technically they are both the same. Do we have a cursor? We have a cursor. Okay, I think I know what's going on. So, The time of day clocks are derived from the AC voltage coming from the power supply. So that 9 volts AC, that is used to work out the time of day, even though they're not true time of day clocks. They're not battery backed or anything. They're just very rudimentary. Take your mains 50 hertz or 60 hertz and do a little bit of math, and that kind of gives you a fairly accurate clock. And the SID needs both 5 volts and 9 volts on these machines. On the long boards, it needs 5 volts and 12 volts, which both come from those onboard regulators. But on the short boards, I think the 5 volts comes from the power supply directly, so that 5 volts DC that we get from there. But the 9 volts is derived from the AC voltage, which is then rectified and regulated down to 9 volts DC. The VIC2 on these machines only uses the 5 volts that comes directly from the power supply. So both of these things point towards we've got no AC supply. So believe it or not, these machines will actually work just off the 5 volts, although some things will be broken. If we see our little fuse back here, this is only sitting on the 9 volts AC supply. So if this thing is blown, the machine will still mostly work, but we won't have time of day clocks, we won't have a SID, and I don't think the tape port will work either, because that kind of also relies on that voltage. So I reckon this fuse is blown, and that's the problem. We'll unplug the power supply, multimeter in continuity mode, and that's open. So if we take a close look at this thing, it will actually tell us what it is. It's a 1.5 amp fuse. Should have more of those on hand. All right, brand new 1.5 amp. Better not blow straight away. Yes. Okay, time is good. Cassette and user port bad. Gotta be those ports. And we've got sound. Just gonna give these a bit of a jiggle. Try again. That's better. Right, cool. That is all good. We still need to test the keyboard, so let's get that done. Keyboard, missing a couple of keys. Just don't know what's going on with the shift lock. That's the panic button. Why is that all the way down? Yeah, that's going to be a problem. Oh. I don't think I've ever seen one like this. Oh, it's missing a good amount of the screws. Okay. This has got the carbon contacts on both the PCB and, of course, the keys. What is going... Oh, okay. The spacebar's just dislodged. There we go. Why are you wrecked? Broken? What's that, Christmas? It's dirty, but it seems fine. All right. All I really want to know is, did this not work because that key was stuck? Was there a bigger problem? I think we have the keys here along with the springs, I hope. Got 2 springs, 3 keys, 2 stabilizer thingamajiggies. Those go in there. Stabilizer bar links in through there. Now, the spacebar normally has a slightly bigger spring. I think these 2 must be for those 2 keys.
Okay. We need a spring for this. So it needs to be a little bit firmer than the other keys, but not too crazy. Oh, yeah. Maybe. Maybe. That's all right. Was that enough to solve our keyboard issues? Was it just that one of the keys was constantly being pushed down? Yeah, no, come on. Oh, our cursor is working. Oh, wait a minute. So when shift isn't being pushed down, this cursor should be down. When you've got shift held down, the cursor is up. But if I push this, you can see our selection is actually moving up. And it doesn't change when I hold down shift. So that's what's going on with the shift lock key. It must be stuck on. We're going to have to borrow another keyboard. Right. That's what it's supposed to do. Cursor key is supposed to move down. Okay. So it just rules out an issue with this board. I don't think any of these wires are being swapped around. How? Oh. Equals works. Wait a minute. It's just the return key doesn't work. Keyboard's not proper broken. It's just a couple of keys that you kind of rely on to do stuff that are not working. Yeah, it's not... Oh, it is a cable problem. No way. Okay, it's a cable problem. Idiot. More contact cleaner for you. Trying not to get contact cleaner on these contacts, because part of the idea of that thing is to move, carbon buildup and such. Exactly what you don't want to do with carbon pads. Bad contact or broken wire. What's it gonna be? Broken wire. Yeah, broken wire down this end. We need to go back to the internets. Alright, W is when row 1 and column B are connected. We had issues with return, which is also on row 1. Okay, 1 seems to be the one that we're having issues with, and that's pin 11 on this connector. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It is the red wire. So we're going to have to cut the red wire and hope that things don't blow up. Contact looks fine. Okay, do I have more of those type? Yeah. Okay, before I cut that off, I want to make sure this is actually dodgy. Have something there, see if we can find it over here. It's that one. Oh, yeah. Okay, before I go cutting things, just in case it's just bad connection where it's crimped here, jam some solder in there. Maybe just needed a little bit of help. Arrow. Yes. Q, W. Yep, it was right at that crimp terminal. Oh, that's just bad crimping. It's not trying to go up anymore. There's only like 3 screws in the back of this keyboard, so not expecting it to work every single key. I saw that shift lock. I saw ya. Okay, come back to that. Okay, cool. One last little treat then. Let's have a look inside one of these shift lock keys. Pop out from the front. Yep, looks pretty standard. All right, what we need to do is just get rid of all this excess solder on the back here. With those cleared off, we should be able to release these little tabs. There it goes. First of all. Second of all, we need to clean the bit in between here, which, as you can hopefully see, is a little crusty. Think about how this goes back together. It's got to go that way. Make sure those go back in. Spring looks good. Oh, step back in there, you horse. All right. It still locks. Hopefully it still shifts. Here we go. I want to see if the shift lock is still being a bit flaky. Ah, that's perfect. This one is done. Did we have any bad parts? I don't think we had any bad parts in this one. Just a few bad connections and a broken fuse. That was it.
All right, that is it. If you've made it this far, thank you very much for watching. These 3 machines are now fully operational. Obviously, this one needs an arrow key, a CIA, and a SID. And this one over here, the eagle-eyed amongst you may notice that it is not the same 64C that we were just looking at. I had to sort of improvise here because the original computer is now back with the owner. Likewise, this power supply is not exactly the same one that we saw at the start of the video. Both of those things are back with the original owner, and they left me with these parts to play around with. It's a long story, but they basically came across all this stuff in one of their family members' previous possessions, and they wanted to get at least one of these up and running. And through various Discord servers and stuff, they came across my channel and got in touch with me, and here we are. So yeah, I'm glad I could help that person out. They're also a patron now, so they're also helping me out. And on that note, a massive thanks to all the people that support the channel on Patreon. If you want to do the same and help me continue making videos like this, please consider signing up using the links in the video description. They also get ad-free early access to all videos, along with discounts on the Lectron store and some behind-the-scenes content as well. Alternatively, a like, share, subscribe, all those things also really help out the channel. So thank you all for watching. I will catch you in the next one. Bye.